Thank you for the introduction. So let's start with a look at the general computational stack. So software runs on operating systems which operate on hardware. Performance, especially the performance of the input-output operations, or I/O, is crucial at all levels. The hardware community developed modern hardware such as persistent memory or new NIC cards that reduce I/O latency. And the operating system community has proposed advanced file systems that avoid redundant I/O. So to maximize the benefits from these infrastructures, it is important to use them in the right ways. So our research focuses on adapting user applications in response to the advances in the operating systems, especially with I/O tasks that involve file or network data exchange. These tasks are prevalent in modern applications. So when the underlying computational models evolve, how do we adapt applications to efficiently use these new I/O interfaces? So let's see why some existing interfaces like read, write, open need updating. These POSIX interfaces are essential for many applications, like web servers and email clients, but they are outdated due to the advances in computational speed and capacity, which makes the original assumptions, such as that the memory is significantly faster than I/O devices, no longer hold. So today, the operating system community suggests replacing them with modern I/O interfaces, like get, put, pig, which we will discuss soon. So these new APIs can make applications run faster. So we aim to automate the migration across different I/O APIs while providing correctness guarantees. So our system is called Sprout. It takes a specification from the API experts and an existing program that uses old APIs, then synthesizes a migrated program, then uses the new APIs. We next talk about how Sprout removes old APIs from the existing program. And this process has been difficult due to three main challenges: the semantic mismatch, complex control flows, and program state interdependence. I'll explain these challenges and how we address them. The first challenge is the semantic mismatch between different APIs. For example, the read API copies a certain amount of data and updates the file offset. We may want to migrate a program to use the get API, which copies an entire file content. But these two APIs differ. So to address this challenge, we break down APIs into atomic operations to help us reason about the semantics of APIs that are similar but not identical. For example, the get API semantics consists of connect file, transfer, and disconnect. So if we were to replace the pread API by get, we would need to remove the code that performs connect file and disconnect. And another important concept is the semantic types. So programs using I/O APIs often have variables that fall into distinct and well-defined categories, such as file descriptor, offset, and size transferred. We attach semantic types to the variables according to how they interact with I/O APIs. For instance, we attach the semantic type size transferred to the return variable of the function that performs transfer. So each atomic operation emits an I/O behavior. For example, these two code snippets use different APIs but emit the same I/O behaviors. So they are behaviorally equivalent. The code on the left uses POSIX APIs, open, period, and close, and the code on the right uses the get API. We see two programs are behaviorally equivalent if every pass in one program is equivalent to a pass in the other program. The loops are unrolled only once. So the next question is, how do we ensure a pass behavior remains the same after migrating to a new API? So we construct the finite state machine for each new API. So here's the state machine for the get API. It starts at the state S0 and takes a connect file operation subject to the requirement that file permissions include read access It next takes a transfer operation and a disconnect operation subject to their requirements. Then it reaches the final accepted state S3. So accept means that the statements on the past are behaviorally equivalent to the new API. So another challenge is that the real-world programs often have complex control flows with branches, loops, and multiple calling contexts. But multiple related API calls may be scattered in different locations. So we need to simplify the program structures. For example, to handle the multiple calling contexts, we introduced the concept of alias function for intra-procedural analysis while preserving external calling information. For instance, the XM open function is aliased with open because it simply calls open as long as a specific condition is met. So we call this condition a liftable condition because it is based solely on a parameter and can be handled in the caller function. Thus, we can bypass analyzing the body of the XM open function while still preserving its semantics. The third challenge is the interference from various statements and interdependent variables. For example, here we may want to migrate the calls to APIs 1, 2, and 3. However, the input parameter of the API 3 depends on computations in the middle. So to determine whether these sequences can be migrated, an in-depth analysis of the program states is needed. So we perform I/O state inference backed by flow and field sensitive point analysis to automatically infer program states. We formulate the intermediate state that contains points to results, semantic type maps, file offsets, and loop contexts. And we formalize the inference rules in the paper. Due to time constraints, here we illustrate it in an example. So here, the top left color is the specification, and the top right is the state machine for the gate API. The bottom left is a C program that we plan to migrate. And in the bottom right, we will be updating the intermediate state during our analysis. So the program invokes a set of old APIs. For example, the call to the XM open function contains 3 IR statements, a node, a call, and a store statements. So first, the node statement updates the points to relations by making the variable SS1 point to the abstract object O1. Next, the call statement returns a value and assigns semantic types based on the spec. Because the specification says that the specification says that the API performs connect file. So the return type becomes file descriptor, and the parameter becomes file path. This result enables a transition from state S0 to S1 in the state machine. So finally, the store statement also updates the points to relations. And for the call to the read API, the process is similar. I'm going to skip the animation because it's similar to the previous slide. But the point is that we update the points to results and semantic type map, leading to a state transition from S1 to S2 in the state machine. Similarly, for the call to the close API, we also update the intermediate state, then transition the state machine from S2 to S3 according to the spec. So after the analysis, we obtain the intermediate state as on the right. So from here, we extract the semantic types into the semantic variable context as on the left. So we next use these results to synthesize the new migrated program. So first, we remove the minimal code fragments that cause the state machine to transition to the final state. Then we insert a sketch of the new API and the call side to read. Next, we complete the sketch according to their semantic types. But before the code compiles, we need to propagate the effects of the deprecated variable fd. So next, we trace the impact of removing the variable fd through value flows. and find two related statements and then need to be removed. For example, here we need to find a replacement for the removed statement. We find that the IO function stat is behaviorally equivalent to the function fstat. So we insert the sketch for stat function and fuse the host again based on the semantic types. Once the synthesis is completed, we get a migrated program that is behaviorally equivalent to the original one. So our algorithm is sound. In other words, whenever Sprout produces a migrated program, the migrated program has the same behavior as the original one. Our benchmarks range from hundreds to hundreds of thousands lines of code, averaging about 10,000. Sprout identified an average of 202 variables with semantic types per benchmark. And the average migration time is 154 seconds. So we also evaluated how much faster the migrating programs run. We used the new hardware such as NVM, emulated by DRAM within a virtual machine. The average performance gain was 38% per benchmark. Please refer to the paper for further details. So here's the, in conclusion, we present a novel approach to the API migration by addressing 3 key challenges. I'm happy to take questions.
Questions?
Hi, thanks for the talk. So your evaluation looks quite impressive. I was curious if you submitted any pull requests to these projects to actually migrate the APIs based on the results of your tool?
Sorry?
I was curious, so it seems like your work has very big practical applicability to migrate these APIs. Do these APIs actually exist in the sense that you could create pull requests for these tools for certain like real-world programs?
Yes, these are real-world programs. The APIs are real-world too. So the APIs are connected from the papers published in some system conference, such as the SOSP, OSDI. So, yes.
Okay, so I guess specifically my question is, did you consider making pull requests to projects to like update with your refactored code?
Yeah.
We can discuss maybe later. Yeah, thank you.
Hi. I was wondering if your high-level approach is also applicable, is also generalizable. Like, do you have any thoughts about that? Like,
yes, we have a section talking about the generalization in the paper, and we generalize to the database domain. We have extra experiments on there.
To which domain?
Database. The database APIs.
Okay,
domain.
databases. So, but I guess you believe that in general, the approach should be generalizable to any particular domain.
So it's all about the specification as a state machine. So if your APIs can be broken down into the atomic operations, and you can define your own state machine to ensure the soundness. So, yeah.
Perfect. Thank you.